Hi, today we are going to talk about the analysis of video content distribution, infrastructures, and the effects on the delivery performances. I'm going to start here by talking about the overview of our research topic. So with the rise of social media platforms such as Netflix, YouTube, Facebook, or TikTok, the video content is being more and more increasingly powerful day by day. And these platforms operate on a scale where video data needs to be quickly accessible 24 hours a day and 7 days a week from around the world, where millions of people are watching hundreds of thousands of videos at the same time from different kind of devices. One of the biggest challenges uh, has been to be able to render thousands of videos at the same time on all the servers. For instance, thousands of people upload the videos on YouTube at the same time, and YouTube faces challenges such as video rendering to their servers and allowing videos to be retrieved back for watching. On YouTube, it allows you to upload videos with videos with long length and different sizes. It does not really limit you on what kind of video you can upload. So since thousands of people are uploading the videos with hundreds of millions of videos size, uh, and they are in like different format and things like that, uploading from slow internet speed or fast internet speed. So there's very high demand for more performant and efficient architecture design in regards to how video content is stored and retrieved. Here first, I'm going to briefly talk about the history of video storage. Not so long ago, some of the main sources of the video storage used to be like CD or floppy disk. CDs and floppy disk could only carry a very small amount of data. Most of them used to be like, some of them used to be like 5 MB, which only supports CD, I mean the music, and they're not that big size. So with the videos quality increasing every day, the size of the videos also increased. Therefore, more storage or better infrastructure was needed. And the modern advancement in hardware storage and manufacturing in the recent year has allowed the video content of high quality and the size to be efficiently stored and retrieved faster on different kind of infrastructures. And so the objectives of our research is to perform experiment on the video delivery performances on different computer architecture. For this research, we will perform the sets of experiments using a few different video encoding APIs, and we'll be using different types of CPUs, memories, and the operating systems. And we'll talk more about this later in this presentation. So before we talk about the experiment, here are a few definitions that we'll be using throughout the presentation. The first one is FFMEZ. This stands for Fast Forward Motion Picture Experts Group, or MPEG. And the other terminology we'll be using throughout this presentation is NRACO. NRACO is a company which is focused on making the reusable components for .NET technologies. They provide NuGet packages for Visual Studio projects. And some of their free services are mostly used with the .NET framework and only run on the Windows platform. And some of their paid services are cross-platform. But for this research, for our initial research, we will just be using the free version on the Windows machine. But we'll talk more about this later again. And methodology. Using the FFmpeg wrapper class provided by Enrico, we have designed a console app which takes the video input and that passes it to the encoder and writes the results back to a output file location. The output file can be any file, and input can also be any file. But we'll be using the .mp4 file and .mov file formats for our initial testing, initial research. And once the video is passed to the encoder and we get the result back to the output file, the processing in the meantime we will be recording the time, the processing time, which is measured using a stopwatch class that is started when the input video is loaded from the drive into the memory, and it runs until the write back is completed. So the processing time encompasses both the memory architecture and the CPU processing. So throughout the research, we'll be using other video renderings APIs with different rendering techniques. But here on today's presentation, we'll just talk about a few of those. Just one kind of video rendering API that we used in just a few of the infrastructures. Okay, so these are some of the hardwares that we are planning to do our research and experiments on. The first one is the Windows 10 machine, which we'll name it Windows 1 machine because we also have another Windows 10 machine. The first Windows machine has the Intel Core, the CPU of Intel Core i7 6700 CPU at 3.4 gigahertz, and it uses the 4 cores and 8 logical processors. And it has the random access memory of 6 GB, and the storage type is hardware hard drive with 1 terabyte of storage, and it has the graphic of NVIDIA GeForce GT 720. Next, we have the second Windows 10 machine, which is also i7, but it has higher CPU with i7 8750H at 2.2 gigahertz. And memory in that machine is 24 gig, and it uses a different type of storage than SSD, which is NVMe of 1 terabyte. And for the graphic, it uses NVIDIA Corporation GP104M, so that is GeForce GTX 1070 mobile. And the other machine we'll be using for the experiment and the research is the Ubuntu 20.04 operating system, and it runs on the Intel Core i7 8570 with 2.2 gigahertz. And the memory type is same as one of our Windows machine, which is 24 gig of RAM and 1 terabyte of NVMe storage. And it uses the NVIDIA GeForce GTX 1070 mobile. And another machine we'll be using is Mac OS 12.0, which uses the Intel Core i7 2.8 GHz quad core, and it runs on 16 GB RAM and 250 GB SSD. The graphic of this machine is Intel SD graphics 630 1536 MB. So with using different kind of operating systems such as Windows 10, Ubuntu, and Mac OS, and using different core and processors and storage type and the graphics, we will be running different type of videos and different video sizes, and try different API, different encoding APIs, video encoding APIs, to do our experiment. And using these four kind of machines, I think we will get a lot better result for our experiment, and it will help us reach our goal closer.
Hello everyone. Just to continue the presentation, next up we have the experiments in software that we were using to do our testing. So it's a simple .NET Core or .NET console application, and we use the Nguyen video converter library. It's a wrapper for the FFmpeg standard library. So just to quickly run you guys over the code, it's pretty simple, very straightforward. We first initialize a FFmpeg converter class, and then we provide two sort of parameters. One is the input video file path. As you can see there, we are testing on, this is a relative path, so it's going to be under /file/sample video resolution. It's going to be the 2 megabytes that we're starting out with. It's going to be an MP4 format. And then the output video path is going to be where we want to store the output video and also the name of the file that we wanted to name. So we called it output _2 megabytes.mov. And then we also, for time measurement, just to measure how long it takes to execute, we initialize the stopwatch class. And as you can see, right after that, we started the stopwatch, which basically means start the time here. And then we do the conversion calling convert media, and we pass in the input video, the output video, and also the format with which we want to convert it to. And then once that's complete, we output the console, just letting the user know it's finished converting, and then we stop the stopwatch. And then in order to get the time to do the conversion, we access the stopwatch variable elapsed, which basically outputs the time it takes. And here are some of the results in the 10LC format. We tested it using files that break the sizes 2 megabytes, 10 megabytes, and 30 megabytes. And then we also tested on 2 different Windows 10 machines. As we discussed earlier, the 2 Windows machines had different specs. Overall, one is generally faster. Overall, one is faster than the other. It had more cores, faster speed, more RAM, faster hard drive. But as you can see on the table here, the first machine for 2 megabytes took 4.439 seconds, and then the second machine took 2.15 seconds. Similarly, for 10 and 30 megabytes, it's 13.3 seconds to 8.6 seconds. So it's obvious that machine 2 is significantly faster than machine 1, despite being running on the same operating system. They had different CPUs, just a different computer architecture. And we weren't able to test on a Linux machine or a Mac OS machine because of the limitation of the library. At the time of testing, the library only supported .NET Framework, which is exclusively Windows, only runs on Windows, so we weren't able to port it to Mac or Ubuntu or any other Linux distribution. So there's another slide after that with what we plan on doing to overcome that issue. Moving on, these are some of the analysis we pull from the results. So the main thing is window, the first machine performed better than the second machine, and there are a couple of reasons for that. The major ones are the difference in the number of cores, the memory size, and the storage types. Machine 2 had more cores. It had, I believe, 6 cores, um, which basically allowed the program to take more advantage of parallelism. It also has a larger memory. I believe it was close to 24 gigabytes of memory versus the 8 gigabytes of memory on machine 1. So having a larger memory capacity allows the program to take more advantage of it. And also, I believe the main and major contributor to the difference in terms of performance is the storage type. So machine 2 uses NVMe storage, and machine 1 uses traditional hard drive, HDD drive. And a typical hard drive takes read and write speed takes around 80 to 160 megabytes per second, while an NVMe drive takes at least, starting out at least at 2,000 megabytes, and it gets faster from there. And the reason why this is very important is because during the conversion, the file is stored on local storage. So there is going to be a read operation that takes place to pull the video file from storage into memory. So that is a hardware dependent operation. So the speed of the hard drive or the storage device is very important in determining how long or how quickly the conversion takes place. And also, after the conversion is completed, it needs to write it back into a file, or another video file back into the storage disk. So that's a write operation. So I believe the main overhead here is going to be writing and reading from the disk into memory. Even though there was a clear distinction between the performance between the two machines, there were a couple other things we did not take into account. For example, like other processes that was running on the machine. We all know that you can't run an infinite amount of processes. The CPU has to basically schedule resources according to which processes needs it the most. So we didn't take that into account. So there could be processes that was running on one machine that was hogging the resources, and it might interfere with the performance on that machine compared to another. So that's something we have to consider for future testing. And some of the related works is YouTube. YouTube is one of the main provider of video content. We watch it every day. In this world, they have to basically cater to and be flexible with a lot of different file formats, but then also at the same time be able to efficiently store and retrieve them. Right? So that is one of the challenges they have to face. And so the way they store, retrieve, and process video data is very important in that line of work. And also, besides video conversion, there's also video compression. So we typically see videos stored just as video files on our storage device, but on large scale applications, they are typically not stored that way. It goes through some sort of video compression steps in order to store it more efficiently and basically take less space, and so they can take more advantage of the storage device. Looking ahead, these are some of the next steps that we are planning to move forward with. Finding an alternative code library that is cross-platform, so we can do testing on Ubuntu, Mac. Also do more testing, and then also normalizing the test environment, right? Because we did have that one issue where we didn't take into account the different processes that was running on the machine. So for future testing, we are planning to normalize the testing environment, so make sure that no other or as much of the external factors are not influencing the result as possible. And here are the references. Here's the link to the FFmpeg wrapper for video encoding, and this is the research paper.